this actually works. It's a weird screen resolution on these Sonys.
And it's open also 1.0.
Yes, well, as I said, I curse at it every 2 minutes.
So what we have here is Matthew Dillon's, and well, actually, that's who we have here. What we have here is DragonFly and a copy of X11. What window manager are you using?
FEWM2, of course. Because I like simplicity. I don't like the window manager
Then what's all that
for me.
crap on the screen around the window edges?
Oh, that silly thing it insists on a title.
Oh wow, the fonts actually came out.
That's a fucked up window manager, isn't it?
Hey.
All right, so first of all, I'd like to thank you for all staying so late. It's going to be 11 before we finish. I'm Matt Dillon. I'm the founder of the DragonFly project. It's in the BSD family of systems. And for the last 2 years, we started with FreeBSD 4. For the last 2 years, I've been spouting theory and rewriting the operating system, basically. And so what this talk is about are really presenting some hard numbers, the first real hard numbers that I've tried to put together on the MP, the SMP mechanisms that DragonFly has implemented. It's just getting to the point where I can actually run numbers on the operating system rather than just spout theory about how cool it's, and how efficient it is. DragonFly is taking a fairly, and I'm glad it fits on the screen, DragonFly is taking a fairly a radical approach relative to the other BSDs on MP. We're developing algorithms that are naturally CPU localized in order to avoid locks whenever possible. An example of that would be a thread needs to access its own thread structure in the kernel. We're talking about the kernel here. It can just do it. It doesn't need, it might need a critical section at most. It doesn't need any kind of MP lock or spin lock or anything like that. We've removed non-critical elements from critical paths. For example, when you switch threads or switch processes, it doesn't go and figure out the exact time down to the microsecond that process was running in the switching path. We avoid cache contention. It's kind of a natural outcome of a CPU localized algorithm. Sometimes locks are necessary. I'm not rabid about removing them. There are times where spin locks are necessary, and we use them there. CPU localized algorithms tend to exercise the same code path. It tends to be the same code, UP or SMP, which makes it a whole lot easier to test. Because you can do 90% of the work on UP and not worrying about MP bugs. And the last 10% is MP, and that's, those are the bugs that you have to find and fix. So I did this test on an AMD Athlon 3800 plus dual-core CPU in just one of those new shuttles, which took a while to get working, but we got it working. 2 gigahertz clock. The intention is to test algorithmic performance, not necessarily throughput. And we really can't, with the tests I've done, I really can't test algorithmic throughput because the onboard Gigi Ethernet doesn't work, so I've got an Intel Gigi card in a standard PCI slot. So obviously I can't test throughput.
You guys Broadcom, right?
No. This shuttle, it's an NVIDIA Ethernet chipset.
Wait, hold on, is this a one or two CPU with dual core?
One physical CPU, dual core.
All right.
This is AMD's Athlon. It's not their optimal dual core, it's their Athlon dual core. So this is their, quote, low-cost dual core, which is still $300-something. But still, dual core, and you get pretty much the same performance. So it's nice. We have KTR, originally developed, I think, by the FreeBSD folks, and I don't know if they lifted it off anyone. What? BSDI. Oh, BSDI? Okay, originally developed by BSDI. Kernel trace logging, it's very simple. You have kernel procedures, and you just have a routine, log, boom, keyword, arguments, and it logs it in a very fast, MP-safe way. The first test I did was, well, how long does it actually take to call kernel trace log function? And that's what this is, because I had to try and subtract it out of all the future results. I did some logging tests with just a string, and logging tests with string plus arguments. The times are, I think everyone can read them. Basically, without arguments, it's on the order of 40 nanoseconds. So that's what I subtracted from all of my other time event results to try and get something approximately, what the actual timing was. The event logs the delta time from the previous event, so the time for the first event is irrelevant because it's relative to whatever the previous event was, which could be anything. I'm going to characterize, I think I can fit it in, I'm going to characterize 6 or 7 subsystems here. I was kind of interested in how long it would take to do this critical section enter exit. IPIQ messaging, which is the inter-processor communication messaging mechanism that DragonFly uses. Your standard T-sleep wake-up, which even if you've got a core scheduler that can switch very, very fast, you still have an abstraction that you have to use in most of the kernel code in order to use that scheduler, and that's typically some kind of generic sleep wake-up mechanism. The slab allocator's free path has to potentially do an IPI, so I characterize that. The malloc path is completely lockless and MP safe, so I didn't bother, but it's about the same time as the free. And then I wanted to characterize packet overheads for the EM interrupt, that's the Intel Gigi driver, and also for TCP processing, since we've got those abstracted into their own threads. So I've got a combination of pretty pictures on the left, except for one slide, and the actual timing numbers on the right. I tried to pick, I got hundreds of results. I tried to pick ones that looked reasonable, that were a reasonable approximation of all the results. So the first thing I wanted to test was our critical enter and exit code. This is a CPU localized function. It simply prevents an interrupt from occurring within the critical section. And it doesn't actually prevent the interrupt. It uses the, I don't know who first developed it, but inherited from FreeBSD4. They had an SPL mechanism that simply flagged some memory, and if an interrupt occurred, it recorded the fact that it occurred and returned immediately if you were within a critical section. We essentially do the same thing. So there's no SCLI or STI. It's all standard instructions, which means it's eminently cacheable in the instruction stream. I ran 100 iterations per test, and it came out to some really small number, 9.5 nanoseconds for both the critical enter and exit call. So about 4 nanoseconds for each. And it's like 3 or 4 assembly instructions for each, something like that. So I said, well, okay, that's good. That's what I wanted in DragonFly. I wanted the code to be able to do a critical section pretty much wherever it thought it needed to without having to worry about performance issue. Probably the simplest and yet most complex subsystem, if you could call it both, in DragonFly is this low-level MP messaging mechanism. It basically is a function you call. It says function call target CPU function argument, function pointer argument, and then the target CPU will do a callback function with argument whenever it gets that. It's an asynchronous mechanism. It's not synchronous. So when you send an IPI from one CPU to another, unless you specifically want to wait for it to be received on that CPU or wait for a result, it's a totally asynchronous mechanism. You could arrive at that other CPU and be processed at any time, from 1 microsecond to a millisecond, depending on what that other CPU is doing. I wanted to do 2 tests. I'm quite fond of end-to-end tests because an end-to-end test covers all of the overheads related to an operation, even if you aren't specifically logging that overhead. So the first test I did was a ping pong. Oh, and before I get into this, the DragonFly abstraction for IPI, inter-CPU messaging, uses a software FIFO, just a tail chasing, separate read and write index, totally lock-free, crossbar across all the CPUs. So if you send an IPI message and you send another one immediately after the first one and the third one after that, there's only one actual IPI interrupt will occur. And I do some tests later on. Actually, I do, might be on this slide. The first test I did was an end-to-end ping pong. You send an IPI message to the target CPU, and the moment its function gets called, that function sends an IPI right back. And it does that a couple hundred times. And I recorded the time it took to do the end-to-end, and you can see, oh, another little note here, the TSC on this Athlon, well, it's not synchronized between the two cores, which I found rather odd and surprising. So there's some drift, and you can see that drift in the results up here. The one direction is slightly slower than the other. In fact, both directions are the same speed. It's because the TSCs were drifting, and I'm only resynchronizing them 10 times a second. What the ping pong test shows is it takes basically a microsecond. That includes all interrupt overhead, APIC overhead, everything. A microsecond to get from a function that wants to do something on another CPU to that other CPU actually being able to do that thing. And I was quite impressed with these numbers. What it means is, well, one of the things it means is it's really, people working with MP who haven't worked with MP before, you kind of think, well, you're sending a message to another CPU. That must be really expensive. And it's expensive in some ways, but in all practical matters, unless you're sending 1 million messages a second to another CPU, it actually isn't as expensive as you might think, and this really bears that out. This is the cost that's basically shared between both CPUs. I mean, 500 nanoseconds on each CPU, and actually it's even less than that because most of that overhead is the APIC getting the message from one CPU to another. The other test I ran was a pipeline, just to make sure that our IPI messaging system actually was pipelining properly, and it turns out it is. That, I just send 3 IPI messages in a row. The first one takes a little extra time because it's, well, actually there's one before. Well, okay, there's some cache effects here. But the gist of this test is that once you've got the pipeline going in the cache, now your overhead is less than 40 nanoseconds to send a message. And by using, one of the things that we're trying to do is we're trying to use algorithms, these CPU localized and threaded algorithms, that aggregate work and take advantage of that. So instead of a free being processed one at a time on a target CPU, if you have a free memory that has to go across another CPU, we want to aggregate multiple frees that might occur within a period of time and process them all at once on that other CPU, because it costs us nothing. One free might cost a certain amount of time. The next one, if it happens right after, it costs basically nothing. This is the T-sleep wake-up test. Basically, thread B is sleeping in a T-sleep. Thread A, this is all on one CPU, is waking it up. It has to do some miscode. Since it's on one CPU, it's not preemptive. And does a switch, and you hit and you switch. So there's a lot of overhead here. We're doing an end-to-end test, so we are taking into account all this overhead, and what we're getting is basically 1.2, 1.3 microseconds total overhead, which is quite reasonable considering that you're doing a thread switch on the same CPU. And again, that's not the core lightweight thread scheduler switch. That includes the wake-up overhead and the overhead required for T-sleep to finish up, and it logs just before it returns. I did the same test on an MP with 2 CPUs, and here you get an idea of what the asynchronous IPI message really gives you. You do wake up on first CPU, and what we get is, put the number here somewhere, here we go. Overhead on originating CPU, 75 nanoseconds, basically in the noise. You can do a wake up. If you're going to another CPU, it costs you nothing because it's just queuing that IPI message and returning. You're going on doing whatever you think. The latency to get to the target CPU is still about a microsecond. That hasn't changed. And you get about 1.7 microseconds of latency on the target CPU. Now, the previous slide, our total latency was about 1.3 microseconds. And now we're at 1.7 going between CPUs. And I was very happy with those numbers. It really means that the wake-up implementation that we have is a completely MP-safe, lockless implementation. There are no locks at all. There's one bus lock cycle for a CPU mask, and that's it. And I'm trying to get rid of that too. All right, I tested free pipelining. What happens is you do a free on the CPU. With the slab allocator, the slabs are owned by a particular CPU, and that's set in stone. Basically, when you allocate memory, you're allocating out a slab that whatever CPU you're on owns, and when you free that memory, that free has to go back to the CPU that the slab was allocated from. This allows the slab allocator to basically operate locally with just a critical section, no spin locks, no other locks of any sort, no bus lock cycles, just critical sections and the IPI. The free path has to use an IPI, and I figured that there would potentially be quite a few frees that have to go between CPUs. So I wanted to optimize that. It's asynchronous. I mean, do you care that it takes a microsecond for the memory to actually be freed after you told it to free the memory? And the answer is usually no. So I found instances where, in the logs, where a number of frees are being done in a row, and I got that time. So local freeze 237 nanoseconds. The frees that have to go between CPUs were 318 nanoseconds on the originating CPU. And I got a weird number on the target CPU. I got 745 nanoseconds each on the target CPU, and I was scratching my head and saying, well, this doesn't make any sense. I mean, is it a cache effect? Oh, I'm debugging on, I'm copying a pattern into the target. It must be a cache effect. Took that out, still 700 nanoseconds. Well, it turns out that it was the KTR logging itself that created that issue. Because my malloc and free paths were doing KTR logging entries with arguments. They weren't simple entries. It was passing all sorts of information for the logging. So I redid it, and I don't have a nice graphic for this, but I redid it, and I basically removed all the unnecessary KTR logs. I just had the one at the beginning and the end of the free function, and I removed the arguments. And I got a much more reasonable number. In this case, the remote side is down to 359 nanoseconds.
Per.
And that per free, yes, per free. Versus 237 for a fully local free that didn't have to do anything else. And presumably the local frees got cache effects, good cache effects, and the remote free has potentially bad cache effects. I don't know whether it's worth fixing this. I mean, it's using part of the freed memory as a link field. If we got rid of that, there might not be any cache effects. It's putting it at the head of the slab queue. It could put it at the end to give the other CPUs cache time to clear, so you don't have a cache mastership change. There are all sorts of things that we can do there. It might not be worth it, though. That's very fast for a malloc and free. Oh, and I'm doing something. When I was talking about naturally aggregating work to try and take advantage of these cache effects, the free does what's called a passive IPI. What it's doing is it's queuing the request in the software FIFO that the IPI abstraction layer implements, and it's not bothering to initiate an interrupt. It's just leaving it in the FIFO. The next real IPI that gets sent, and the clock interrupt always sends one, will flush the rest of the passive entries through. This is very fast. 178 nanoseconds, 147 nanoseconds, including whatever overhead from when I logged the beginning of the free to when it did the passive IPI. That's perfectly reasonable, I think. And you get guaranteed aggregation on the target CPU, and I think that's very important. Guaranteed aggregation, not statistically it might do it sometimes, it's that you get it guaranteed pretty much. And the result of this is that most of the overhead on the target CPU, you have 1 microsecond taking the IPI, but if you're doing 3 or 4 free operations, that 1 microsecond gets diluted fairly quickly. It becomes very efficient. There are some cache effects, fairly obvious cache effects here. Let's run out of time. 5 minutes? Okay, I'm going to skip the cache effects.
Flush.
Flush. Network overhead, network interrupt, single and multiple frames. So Intel EM device, it does interrupt moderation. So you can have a single packet receive frame, and you can have multiple packets in a single interrupt. I tested both cases. I got some fairly nasty numbers, actually. Single packet overhead is 2.5 microseconds. Multiple packet overhead, where is it? The multiple packet overhead is 1.26 microseconds. I think I know where that's coming from. Quite a bit of it is coming from the messaging infrastructure. We're actually doing a malloc of a message header before we send the in order to encapsulate the mbuff to send it off to the TCP thread.
You can pre-allocate those.
We're going to embed them in the mbuff. That solves the problem completely. So that will probably get rid of 200 or 300 nanoseconds and make it a lot more reasonable. I'm quite interested in figuring out exactly why it's taking
300
so long.
nanoseconds, geez, that's like human almost recognizable.
So I grew up on a Commodore PET, 1 megahertz, 6502.
The disk drives are
So it's
faster.
like, and now we're talking about, it's running basically 1 instruction a nanosecond if it's fully cached.
You had nanoseconds.
One thing that's come out of all these numbers is the cache effects are huge. I mean, whenever you get a cache miss, it's worth 10 or 20 or 30 instructions, cacheable instructions. So this is just going to redouble my efforts to aggregate work as much as possible. TCP packet. Our network protocol stacks are threaded. And they're also MP, but we haven't quite gotten rid of the big giant lock yet. Any input packet is demultiplexed and handed off to the appropriate protocol thread, and there can be a protocol thread like TCP has a thread on every CPU, basically. They're demultiplexed based on address and port, so any particular TCP thread will always get the packets for a particular connection, which means that the TCP threads are completely lockless when they're processing a TCP, which is very important if you're processing a heavy workload, because you don't want to have to do a spin lock because you're processing 100 different connections. You don't want 100 different spin locks.
Matt?
Yeah?
Somebody over here wants to ask you a question.
Oh, sure. Just interrupt if you have questions. Am I the last?
Hey, look, he's interrupt driven.
Okay, I'm interrupting. Go ahead.
Okay, so I'm more familiar.
I'm talking fast.
More familiar with the feedbacky side of it, so just ask a question.
Could you repeat the question?
There are fast interrupts in the drivers, like that take the packet all the way up the stack, or.
I didn't quite understand the question.
He wants to know whether or
are
not
the
you drive
interrupts-
the packet to completion to the top of the stack.
In one
In one
At the interrupt.
in one interrupt? Well,
Like
okay.
LRP.
We're talking about preemptive and non-preemptive threads here. The interrupt thread in this case is a preemptive thread, which means when the packet comes in, the interrupt thread will preempt whatever the thread is running, unless it's in a critical section, run. But then the packet, the TCP thread is scheduled normally. It's not a process, it's a thread, so it has a high priority.
Do you do stack handoff between the interrupt and
No,
the TCP thread?
no, it's actually doing a real switch. When it's running the EN interrupt, it's actually doing a thread switch into the EN, into the interrupt thread for that, and doing a thread switch out. I'm not doing the BSDI stack sharing idea or other. Because it turns out not to be a real big issue. I mean, if you're working on algorithms that are aggregating, they're trying to aggregate work, then the overhead for entry and exit is not a big deal. Okay, I've got some conclusions here. I pretty much talked about most of them. Let me just talk about, well, let me go through one or two. Is that okay?
The audience got some particular questions for him in addition to what's already been
Maybe
asked.
I can go through these as their questions if there are any. Does anyone have any questions on DragonFly?
Have you run these tests under like stock 4.4, stock BSD?
No,
BSD?
no, I haven't done any KTR logging type of thing to compare it against
It'd
previous.
be interesting to see how, the benchmarks, be able to compare it to the benchmarks.
I think the real issue when it comes down to the algorithm is whether the work aggregation idea reaps real benefits with the cache effects. We're talking about, well, in conclusion, even a medium complexity procedure such as processing TCP packets still takes much less than a microsecond typically. And there are very few procedures in the system that take more than a microsecond. But when you start chaining them together, now you're getting into multiple microseconds and potentially cache effects. And the question is, where is that demarc point?
You mentioned that the TCP threads don't have any logs, or I guess for the TCP/CPs and stuff like that.
Correct. Everything runs in the context.
What about control messages, like you want to create a socket that might be on another TCP?
Jeff could explain that better, but we have wildcard sockets, and right now they're handled by CPU 0, I believe. Is that correct?
Actually, they handle an all CPUs, they're replicated. So we partition.
Well, that's right, we put in the replication
Yeah,
here.
so we replicate listening sockets and we partition
Right.
bound connection.
So if you have a listen socket, you do a listen command, that's a wildcard socket, basically. It's running on all the CPUs, TCP threads. And when you get a packet coming in that's a new connection for that, it gets demultiplexed based on its port and address to one of those threads, and either one can handle the accept.
Are you starting to think much about like 4-core or 4 processor and style architectures?
Well, the answer is yes and no. Really, we're a fairly small group, and we only have, I think, 3 people that are running these on larger systems, 4 and 8 CPU systems. I think some of them are new. I don't have the financial resources really to get those kinds of, plus I don't have the power budget. I'm already at the breaker limit for my machine room in my home. And this, by the way, is why I've been switching all my equipment to AMD, because it takes less power. Yeah.
Could you explain, again, for those of us who got lost in all the microseconds and analysis?
Sure.
Could you explain to me why you're doing this? What is the high-level goal you're trying to accomplish?
The high-level goal that I'm trying to accomplish is to validate the theory that the algorithms Dragonfly has been implementing are actually suitable and efficient and appropriate.
And the goal of Dragonfly is to make a grid computer? Or?
You always have to have a goal that you may not necessarily ever achieve, and our goal is going to be transparent clustering, basically.
Okay.
With process migration that works. We're still in the middle of rewriting most of the BSD routines. We're making progress.
So this is a major rewrite of BSD.
Yeah.
Transparent clustering.
Yeah.
Okay.
No shared code base after this.
There'll probably be some, but it's
But
going
it's
to be
all
on the edges. I mean,
high
most of the
level.
core is already, rewritten. The allocator, the
Question in the
scheduler,
back.
everything.
So do you see any of the other BSD projects as possibly picking up some of this and
I
integrating
can
it
see
into
them
their
picking up
kernels,
at the
or-
algorithmic level. I think that they'll be picking up some things, and I think over the last 2 years, some things have been picked up on. I don't really want to get into my complaints and reasons for why I broke off BSD in some of this talk.
Please.
No.
That's for the bar.
Save
That's
for
for the
beer.
bar. It really is.
Nice thick glasses.
Any other questions?
How do you explain the clock drift between the cores when you're understanding
I
the
have no
clock?
idea. The TSC, I figured it's a dual
It's
core
duplicate
CPU.
cores. They didn't bother to bridge it.
I guess they didn't.
That's expensive.
They're using the hypertransport layer between the cores, I'm presuming. Do you know? I'm
believe
sure
so.
they
Is it
are.
possible that it's SMM or SLI events?
No, not for the TSC.
No, the TSC would have to be a separate piece of hardware sunk between them.
No.
Yeah, I think they have separate PL, and it makes sense actually. They have separate PLLs for each core, because trying to synchronize the clock on that much surface area, why when you don't have to?
Well, and they already have problems with that to begin with.
Yeah. So they just have the hypertransport, and it deals with the clock.
I'll talk to you offline about something.
Okay, I'm interested.
Cool. So it looks like there's some people who are interested in a little more detail about that. And actually, I think aspects of this at least look extremely cool. What's the likelihood that some of this is going to end up with some stuff at userland where we're going to feel like things sort of just feel faster for no good reason?
Well, when you're running on a 2 gigahertz machine, any UI other than maybe GNOME is going to feel fast, right?
Right.
You can open up this one, it feels fast. I think it eventually it comes down to features. I mean, these days, there's so much CPU power available that you're not CPU bound all that much anymore. You're IO bound.
You
more
should see
than
the pile of stuff in my office, though.
That's human bound.
I can make things go CPU bound.
How long do you project before before you'll be able to migrate processes between?
It would probably be at least 2 years.
Another 2
We
years?
have to, the next big thing is the DFS and the IO subsystem. We have to convert those from the buffer mapped memory to pageless before we can even contemplate doing any sort of migration. Because
Wow.
the cache coherency layer is the most important and the most complex piece of this, and we can't even begin that until we fix the IO layer and get everything in pageless, because otherwise it's just impossible to do cache coherency layer.
So I'm gonna ask you Jennifer's question, because she always asks this, can we get the slide?
Yes.
Woo.
Oh, and the slides of mine are available on my website too, so they're already.
Excellent. I'd like
I'll
all of
put
the
them on
speakers
I'll put
to
them
come
on
up here.
DragonFly.
It really